morning everyone. In continuation to the previous lecture, here we are going to study the single tone AM equation and the power relations of the amplitude modulated signal. So in the previous session, we have concluded that the time domain equation of AM signal is given by S of t is equal to AC into 1 plus Ka m of t into cos 2 pi fct. So this is the AM equation. This is AM equation where m of t is a general signal that you are going to transmit. Now, if you consider the single tone, for single tone AM, tone is nothing but frequency, right? Tone is nothing but frequency. For a single tone, your message signal m of t is a known signal which is generating only single frequency. Let us say the frequency of the signal is FM and the amplitude of the signal is AM. In that case, for single tone AM signal, the message signal can be written as AM cos 2 pi FMT, where AM is the amplitude of the tone, and this is the frequency of the tone. Okay, so if I substitute this m of t in the above equation, this S of t AM, that is modulated signal, can be written as AC into 1 plus, this is the amplitude sensitivity factor, AM cos 2 pi FMT into cos 2 pi FCT. So now, if you look at this term, absolute maximum value of Ka m of t is known as modulation index. In this particular case, I can write Ka into AM mod as mu. So now if I substitute in that equation, S of t will become AC into 1 plus mu cos 2 pi FMT into cos 2 pi FCT. Always remember that this mu value should be less than or equal to 1. Now, if you look at the different cases for this, if mu is equal to 1, the modulated signal will be this one. This one will be the modulated signal for a sinusoidal signal as a carrier. This is for mu less than 1. If mu is equal to 1, this will be the modulated signal, that is for single tone. And if mu is greater than 1, it will cross the axis, and this will be the modulated signal. This is for mu is equal to 1, we call it as exact modulation. This is for mu greater than 1. Now, if you assume that this is the maximum value of your modulated signal, this is let us say the maximum value of the signal AM, and this is the minimum value of the signal A minimum, and this is A maximum, and A maximum. If that is the case, now if you look at the if you calculate the maximum and minimum values of this particular signal, your A maximum is equal to AC into 1 plus mu, right? And A minimum value you will be getting it as AC into 1 minus mu. So why we are calculating this A minimum and A maximum means the other way of developing the equation for the modulation index. If you look at these two equations, so if I write A max by A minimum, A max by A minimum, this will give you AC into 1 plus mu divided by AC into 1 minus mu. So you will be getting 1 plus mu divided by 1 minus mu. So by using componendo dividendo formula, you can get mu value as A max minus A minimum divided by A max plus A minimum. So in the laboratory, you will be using this particular formula to calculate the modulation index of an AM signal. So the other ways of calculating modulation index is mu is equal to AM by AC. This is the ratio of the modulating signal to the carrier signal. Always remember that. Try to reduce the try to keep the amplitude of the message signal less than the carrier amplitude. So this is the derivation for the modulation index, where it is defined as the absolute maximum value of the KAMO of t, and which can alternately written as mu is equal to A max minus A minimum divided by A max plus A minimum. So now this is the time domain equation of the AM signal. And if you continue with this discussion, so you got S of t as S of t is equal to AC into 1 plus mu cos 2 pi FMT into cos 2 pi FCT. So now this can be extended as AC cos 2 pi FCT plus AC mu cos 2 pi FCT into cos 2 pi FMT. So now this can be written as AC cos 2 pi FC plus, this is AC mu by 2 I can write, and 2 cos 2 pi FCT into cos 2 pi FMT. This is 2 cos A cos B formula. So I can write AC into cos 2 pi FCT plus AC mu by 2 into cos of 2 pi FC plus FMT plus cos 2 pi FC minus FMT. Now this will be called as the upper sideband, and this will be called as a lower sideband. Now if you look at the total power in this particular equation, so this is the carrier component, right? This is the carrier component, this is the upper sideband, this is the lower sideband. Now the total power content in the signal can be written as P carrier power in the carrier, plus power in the USB component, plus power in the LSB component. Now the power in the carrier can be written as, this is the cosine signal, since the power will be root mean square value, that is AC by root 2 whole square plus plus upper sideband AC mu by, already 2 is there, 2 root 2 whole square plus another component is there, AC mu by 2 root 2 whole square. If I simplify this, AC square by 2 plus AC square mu square by 8 plus AC square mu square by 8. So this is nothing but AC square by 2 plus AC square mu square by 4. So this particular thing is the sideband power. Sideband power. That is, the sideband power is AC square mu square by 4. Now if I take AC square by 2 common from this, I can write 1 plus mu square by 2, or else I can write PC into 1 plus mu square by 2. This is the total power contained in an AM signal. In this, the total power is equal to the carrier power plus sideband power. The carrier power is PC is equal to AC square by 2, and the PS is equal to PC into mu square by 2. That is sideband power of the signal. Okay, so this is the time domain equation and the description, as well as the power, how to derive the power of the AM signal. Okay, so now if you look at the frequency domain representation of the signal, now frequency domain equation of single tone AM signal. Now if you consider the signal single tone AM signal in time domain, S of t is AC into 1 plus mu cos 2 pi FMT into cos 2 pi FCT. So AC cos 2 pi FCT plus AC mu cos 2 pi FCT into cos 2 pi FMT. Now here we have a carrier component, we have the sideband component. Since a multiplication of cosine signal cannot be represented as a frequency domain signal, hence I will split it into two summations, plus AC mu by 2 into cos 2 pi FC plus FMT plus cos 2 pi FC minus FMT. So here we have three components, cosine components, so that I can easily convert them into frequency domain by making use of frequency shifting property and delta function properties. By making use of delta function properties, we can easily convert it into frequency domain. So the frequency domain equation S of f can be written as, so AC by 2 into, as we discussed earlier, cos is a combination of exponential. Exponential is multiplied with 1. 1 will constitute a Fourier transform pair with del function, okay, delta of f. Okay, so because of that reason, if 1 is multiplied by e power j 2 pi fct, then in the frequency domain it will be shifted by that much units. So by using that particular frequency shifting property, exponential property or frequency shifting property, so I can write cos function as cos 2 pi fct is equal to e power j 2 pi fct minus e power minus j 2 pi fct divided by 2. So that is the reason why we got 2 over here. So 1 is multiplied by that. So hence del of f minus fc plus del of f plus fc, because of these two exponentials. Sorry, this is plus these two exponential, we got this one. So now this is the frequency domain representation of the first component. Plus similarly here, except this f term, the remaining thing is same. So AC mu by 4 you will get, then del of f minus fc plus fm plus del of f plus fc plus FM for the first term, plus for the second term del of F minus FC minus FM plus del of F plus FC minus FM. Okay, so now this is your upper side band, this is also the upper side band, this is the lower side band component. Of course, this is the upper side band positive component, this is upper side band negative component, this is lower side band positive component, this is lower side band negative component. So you will be getting, if I draw the spectrum, okay, if I draw the spectrum, you will be getting the carrier components at FC. You will be getting the carrier components at FC and minus FC. So this is FC minus FC. This is your S of F. Okay. So now the amplitude is AC by 2. This is the amplitude. So AC by 2 is the amplitude. So this will represent the carrier. This will represent the carrier component of the signal. And if you look at the upper and lower side bands, so this term is over. This term is over. Now, if you look at this term, you will have a delta function at FC plus FM with reduced amplitude. Hence, I am drawing a component here where you will represent FC plus FM with magnitude AC mu by 4. And similarly, you have another component. This component is over. You have a similar component FC minus FM minus off. So you will be getting a component over here. This is FC plus minus off FC plus FM. Right? So this we'll call it as upper sideband positive component. This will be upper sideband negative frequency component. Now coming to this next component, FC minus FM will be less than this FC. Hence, I can write here this component is FC minus FM, and here similarly you'll have another component minus of FC minus FM. This will call it as LSB, a positive frequency component, LSB, a negative frequency component, and the magnitude is AC mu by 4. AC mu by 4. So this is the frequency spectrum of a single tone AM signal. Spectrum of a single tone AM signal, which is having only one frequency term, whereas in case of general thing where you will have a band of frequencies right from 0 to W, here only a discrete frequency terms were there. Hence the bandwidth of the signal can be written as, the bandwidth is given by, so now this will be the bandwidth. So this is the bandwidth of the signal, this is the transmission bandwidth. So if you look at the bandwidth, so bandwidth is equal to what? So upper frequency minus lower frequency minus FC plus FM, and you will get bandwidth of the AM signal. Transmission bandwidth of the AM signal is given by 2 times the highest frequency component, or else here only single frequency is there, you will get 2 times FM. So now in summary, you can say that the power transmission bandwidth is equal to 2 times FM, and the power, total power, you can say total power is equal to PC into 1 plus mu square by So these are the results which we got for a single tone AM signal. Now, if I extend this to multi-tone concept, where you will have multiple number of frequency terms, then we call it as multi-tone AM signal, where you will have multiple frequency terms, right? So now in multi-tone AM signal, this M of t will consist of multiple discrete frequencies. Like you have, let us say, 3 signals were there, where let us say message signal is consisting of 3 tones. So AM1 cos 2 pi F1t plus AM2 cos 2 pi F2t plus AM3 cos 2 pi F3t, where F1, F2, F3 are the 3 multiple discrete tones or discrete frequencies. In that particular situation, your multi-tone AM signal can be written as S of t is equal to AC into 1 plus Ka M of t to cos 2 pi Fct is the general equation. Now I will be substituting, instead of M of t, I will be substituting the respective equations. 1 plus Ka AM1 cos 2 pi Fm1t plus Ka AM2 cos 2 pi Fm2t plus Ka AM2 cos 2 pi Fm3t into cos 2 pi Fct. So now we have 3 different modulation indices. Mu1 is equal to Ka into AM1, mu2 is equal to Ka into AM2, mu3 equal to Ka into AM3, AM3. Now I can write this as AC into 1 plus mu1 cos 2 pi Fm1t plus mu2 cos 2 pi Fm2t plus mu3 into cos 2 pi Fm3 into t into cos 2 pi Fct. Now if you consider the total power, so we have 3 different modulation indexes. So the resultant modulation index, I'll call it as mu t. If that is the case, the total power can be written as Pc into 1 plus mu t square by 2, where this mu t is equal to under root of mu1 square plus mu2 square plus mu3 square plus and so on. How many number of multi-tones are there, that many number of modulation indexes will be defined, and you will be calculating the resultant mu total value and substitute that in the equation. And if you look at the spectrum also, instead of having single tone, you will get a multiple number of tones here. So of course you will have a cos term, AC cos 2 pi Fct. For that you will be getting the spectrum at plus or minus Fc. Delta functions will be occurring at plus or minus Fc. This is Fc, this is minus Fc. Then you will have different components. Let us say this is Fm1 component, this is Fm2 component, this is Fm3 component. Of course, it depends on the amplitude of the signal which you have taken. This is Fc plus Fm1 component, this is Fc plus Fm2 component, this will be Fc plus Fm3 component. So if the condition is that Fm1 is less than Fm1 is less than Fm2 is less than Fm3, if that is the case, this will happen. So these are the various frequency components, negative components. Similarly, you will have lower sideband frequencies. So like this, how many number of components that were there? that many number of delta functions will be generated. So now this is fc minus fm1, fc minus fm2, fc minus fm3, and so on. Now if you look at the bandwidth of the signal, this is the highest frequency component, this is the lowest frequency component, hence this will be the bandwidth. So the bandwidth, transmission bandwidth is 2 times, since fm3 is the highest frequency component, so 2 times fm3 will be the bandwidth required for transmitting the multi-tone AM signal. Okay, so this is about multi-tone AM signal and the corresponding power equation. This is the power equation, and how you are going to calculate the total resultant modulation index for the multi-tone signal. So this is the spectrum of the multi-tone signal. So this is about amplitude modulation and the definition, general form of the amplitude modulated signal, and then we have seen the time domain as well as frequency domain equations of the signal. Then we extended that particular concept to single tone, where a single frequency term is considered as a message signal, and we have calculated the total power required for transmission of the signal. Then we extended that to a multi-tone frequency modulation, where the multiple number of frequencies are considered to transmit the AM signal. So that further we have calculated the total power and the bandwidth required for transmitting the multi-tone signal. So thank you very much. We'll stop the lecture here. We'll continue the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.